In the previous small signal analysis, we assumed that input is balanced, so the amount we go up on the left and the same amount goes down. But in this example, we are tying the other side to the ground, AC ground, meaning DC voltage. So DC voltage, no voltage change. Only small signal variation on the left hand side. In that case, how we are gonna find the gain? Here again, if you only change the voltage on here, that will result in current variation ID. Such current variation can only go through the M2. There is no other path to flow. So once that there is ID there, then voltage drop will be ID over GM. Another voltage drop, source and gate, would be ID over GM. So finally, we can find the KCL around the input loop. So KVL around input loop. We can write down V in minus ID over GM, another minus ID over GM, equal to 0 volt here. So ID equal to what? 2 GM times V in. That this is the first equation, and second equation what? So V out would be V out 1 minus V out 2. Then what? So current through RD would be RD times minus ID, right? And minus and ID times RD. So 2RD times ID minus, that would be second. So from 1 and 2, we can drive that V out would be, I'm sorry, so here the previous case, that's not gonna 2, this is 2 times, so over 2, right? So finally that would be minus GM RD times V in. So we get the, so even with the single input, so AV can be found at minus GM RD, same as the previous the example, the fully balanced input variation, we get the same gain. For this excitation, what we can expect is that since the other side is grounded, we can expect that there is voltage variation. This is not the, in this example, this is not the AC ground. But that results in the same gain, because this input, why we can think of that, so differential V diff would be what? V in minus 0. So input differential voltage is the same. So we can decompose into V in variation into differential component and common mode component. The common mode variation would be what? V in plus 0 over 2. So we can decompose the input, the one-sided input, into two components. So for the differential, we see that AV, so V out would be, we see that V out over V in, V diff is AV minus GMRD. So from this differential circuit, our circuit only shows the gain for the differential component. For the common mode components, there is no gain, right? So that's why we are getting the same the gain derivation, and even though the source node is moving around. This another circuit derivation shows that some other technique to find the gain of this single-ended differential pair. We can show that how we can drive there. there's another way of finding amplifier gain for the single-ended input. First, we can find the gain from input to x, Vx, and then we can also find the gain from input to Vy, and then we can get the overall gain out of those from here to there and here to there. First step, if you look at the resistance looking into M2, that would be 1 over Gm. So we can find the gain from input to Vx. So Vx would be Vin times Gm Rd 1 plus Gm Rs, right? That would be minus. So Rs equal to 1 over Gm. So Gm Rd over 2. The second gain from input to Vy, we would like to find the gain from here. We would like to find the V. Let's say this is the source node is Vs. So we can find the gain from Vx to Vs, and then gain from Vs to Vy. I'm sorry. So V into Vs, and then Vs to Vy. So from V into Vs, the gain would be what? So this is exactly, so from here, this node would be Vs. That node would be this output of the source follow. If you look at this part, so from input to output, input is gate and output is source. So this is just like a source follower. So the gain from, so Vs would be what? Vs would be Vin times what? Gm Rs over 1 plus Gm Rs, because the Gm because the Gm is equal, the Rs is 1 over Gm, so that would be what? So 1 over 2 times Vin. Now, and the gain from Vs to Vout, Vy would be what? So that would be what? The common gate amplifiers, right? So Vy would be what? Vs times Gm Rd, right? So finally, Gm Rd times what? Vs would be half Vin, right? So from from this guy, this part and that part, we can find out that so third equation would be, so Vy minus Vx minus Vy, Vx minus Vy would be the output, differential output, Vout. That would be minus Gm Rd over 2 minus Vin minus 2 Gm Rd times Vin, right? So finally, the AV differential gain would be Vo over Vin, Vx minus Vy over Vin will be minus Gm Rd. So surprisingly, the gain is just like the differential amplifier, even with the single-ended input. The reason why, as I explained before, only the common mode response would be the suppressed, and only the differential input will be amplified. in that case, whether that is single-ended or differential and input, those differential for those cases, differential input is the same as before. Okay. The source generated differential amplifier. Sorry. For the single-ended amplifier case, if you have a source degeneration of RS and RD output, then the gain would be what? AV would be from input V in to V out would be what? GM RD over 1 plus GM RS. Okay, so differential amplifier like here would be similar. So this is for small input variation up and down on both terminal by the same amount, that will create the current, differential current ID. So this center node would not change, the voltage would not change, so it would be AC ground. So you can find the small signal equivalent model like this, single-ended version of the equivalent model, so we can find the gain similarly. Here, something that we have to make sure or want to understand is that the input amplification range, without RS, we know that the input amplification range would be between what? Plus minus root times V overdrive of the M1 and M2 at bias condition. But if you have a degeneration, we know that the gain would be smaller, right? So it will extend, so smaller than without the RS at the small signal sense. How about the large signal sense? What would be the input signal range? Let's say for the extreme case, so older current IS is flows through on the left hand side. On the right hand side, zero current. So it's a zero current. So zero voltage drop across RS2, and voltage between gate and source would be VTH, right? And the left hand side would be VTH plus square root times V overdrive, because it need to flow 2x larger bias current at the ISS. Okay, this is the VP and this is the VN for the input. So we can find out the KVL the network around the input. So we can drive the equation by KVL around input loop. So starting from VP, we have a voltage drop. How much? VTH minus square root V overdrive. And we have a voltage drop across where? RS1. That would be what? Times, I would say this RS times ISS, right? And then how much voltage drop over RS2? That would be 0 volt because no current. And also voltage drop between gate and source of the M2 would be VTH. Now we are seeing minus on that node, so we would have a voltage up, VTH. That would become what? VN. So VP and VN VP minus VN would be what? Square root. What else? What happened? I'm sorry. So that one was plus, right? So plus square root 2 times V overdrive plus RS times ISS. If you look at here, we have an additional term, that extreme case, that we have an extended amount of input range by this amount, RS times ISS. So this portion, this clipping as a maximum, that point would be what? Square root times V overdrive plus ISS times RS. So we have an extended input range, but at the expense of, at the cost of reduced AC gain by like that. So previous we had without RS, we had the AC gain GM times RD, differential gain, but now we have a differential gain of a GM times RD over 1 plus GM RS. So by having reduced the gain, we get the larger input amplification range by how much? ISS times RS. So this curve is a Vx and Vy graph. So this curve is only single-sided. So the actual gain would be the half of that one, half of this guy, right? If you take both x and y, then it would be the gain would be GM times RD. So I'm gonna ignore that fact. So what you have to remember is that source degeneration would give us a larger input amplification range by RS times ISS times RS, that much, and then we have the reduced AC gain like that. So this kind of a source degenerated amplifier has the problem such as the DC drop over RS. At bias, for the same input voltage, the ISS tail current will split in half. So each the ISS over 2 will flow through on the left hand branch. The right hand side branch will also flow ISS over 2. In that case, voltage drop across RS would be RS voltage VRS would be what? ISS over 2 times RS. So it is reducing the headroom, voltage headroom for the input and the output. For example, let's check out the input common mode range, CM range. Because of the RS, so input common mode range, maximum input common mode would, let's say, maximum common mode input range would be the DC, output DC voltage plus what? So in this case, this node voltage would be what? ISS times over 2. VDD minus ISS over 2 times RD, that would be the output voltage of the drain. And the gate would be plus VTH above that drain voltage. So the maximum input voltage would be, so VDD minus ISS over 2 times RD plus VTH. What about the minimum voltage? It would be, so the source node should be starting from source node, that would be overdrive of the ISS current source, and plus the voltage drop over RS, that would be ISS over 2 times RS. And we have a VGS, right, across the gate and source of the M1. So that voltage would be what? VTH plus overdrive, right? So this is the minimum common mode voltage for that input. As you can see here, we have an additional term here because of the RS. The input range is, input common mode range is limited. So input common mode range must be higher than before, right? Also, this is the input common mode range, but also the output range also reduced because of the fix the DC voltage drop across RS, the minimum peak it can go down would be reduced, right? Because of the input minimum input command range is reduced, the output lowest peak will be also reduced. So because the output minimum swing is also related to the input command mode, right? So V min V in versus max V in, right? What about the output range? Yeah, so assuming the output, let's say output range, also find out output range. Output range would be what? So maximum would be VDD and lowest peak would be what? V, and so assuming gain is high, so V input common mode, so input V in CM minus VTH would be the lowest output range, right? Because the higher input common mode range, because of that, right? So we have a limited output signal range. So it is to maximize the signal range under low supply voltage case, it would be important to minimize or eliminate such voltage drop over RS. We can do that by the following way. So this is the split tail current source degeneration. So in that implementation, we know that the source current is split into two branches. In that case, at bias, this current flow and the current between current over RS would be zero current. So voltage drop over RS would be 0. So input common mode range is now recovered, right? Because no voltage drop on the source. But the signal gain and input linear range would be the same, right? So in that case, the maximum input range would be what? So you can assume that all the current is flowed onto one side, then Vp and Vn. The zero current on the right and ISS on the left. So that would give us VTH drop, and here VTH plus square root times V overdrive. And here what? Voltage drop would be ISS times RS, right? So at the extreme input case, Vp minus Vn, that would be what? V square root 2 times V overdrive plus ISS times RS. So this factor is exactly same as before, right? So V out, so that would be Vy minus Vx in that case. If you take it like this, we have a positive gain, and if you take the different way, then we have a negative gain. So let's take it for simplicity. So for positive gain, so in that case we have what a small signal gain would be Gm times Rd over 1 plus Gm Rs. You can find that using the single-ended equivalent model. So single-ended from the undergraduate course, we found that we learned that such amplifier, single-ended amplifier, would be Rs, because at the middle, the voltage middle would be AC ground, because no voltage variation, because the voltage go up and down by the same amount if we assume that is linearized the small signal model. Okay, so this is AC ground, so we can find that equivalent small signal model. Okay. Okay. Now, what about the input? Do you want to find out the input signal range for here? It is the same as just a differential pair, right? So I'm gonna skip that. We can exercise that. Okay. We have other case of load configuration. So as we learned before, we can use that diode connected load, and also we can use that current source load to maximize the gain I up, let's say. So here current source to current source. In that case, the gain would be what? Gain AV would be GM ROP in parallel with RON minus or positive, whatever. So in that case, the problem with this kind of amplifier is that even though we can have a maximize the gain that we can get from a single transistor, the problem is at the bias condition, the ISS flow on both branch and ISS over 2. So if there is so at bias there should be I up and ISS over 2 must be balanced. So that the output voltage, output common mode voltage is well defined. Well, but if I up and ISS over 2 are not exactly the same, but this is a typical case. We cannot guarantee the pull up current and pull down current exactly matched. It is almost impossible. In that case, any small signal mismatch, the delta current will flow through, let's say ROP and RONE here. Any small current mismatch here will flow through that high output resistance that will create the output voltage either to VDD or near to ground. So small delta I, I up minus ISS over 2 will flow through the high output resistance, meaning ROP by RO and ROP parallel with the RN. That gives us not well defined output voltage. But if you look at this kind of a diode connected load, however, such impedance is very low, 1 over GM. Even with the small current variation or mismatch, the voltage we are seeing here at the voltage variation would be very small. So typically low impedance amplifier, low impedance load with the low gain amplifier is easy to bias, like just like this is okay. But high impedance like ROP and RON are seeing each other for pull up and pull down like this and fighting each other. In that case, we cannot use this kind of amplifier by itself without common mode feedback and common mode negative feedback. So we need the help of the negative feedback to find the proper bias level VB by monitoring those two output level. So we find the common mode voltage R. So R we put a very high impedance resistance at both and take out in the middle to find out the V output common mode. So drive that loop, the output common mode voltage level is the desired level like VREF. In that way, we can have we can adjust the VB so that to find the proper IOP to exactly match ISS at the desired output reference level voltage. So this kind of high gain amplifier is difficult to design. I mean, you need you need extra circuit. Actually, you need extra circuit. Okay, so this is very important to understand when you need this common feedback or not. So whenever you see like a low impedance load like 1 over GM, you don't need. But for high impedance like a current source load, you definitely you need common feedback. Okay. For differential amplifier, just simplest common feedback amplifier structure is like shown here. We add R1 and RS at the output and take out the common mode level and bring that voltage, common mode voltage, to the gate of the load current source. That way is self-feedback, self-negative feedback, feedback loop that construct common mode feedback. Okay. The gain of this amplifier is that at the bias, this is H output common mode. So for input differential input variation, we will create the differential current ID. That would be voltage generation between gate and source would be ID over 2, and this differential current would be, so I'm sorry, ID over GM. Here voltage will be ID over GM, right? So that current will flow through R1 and R2 because that R4 and R3 is just current source. A DC voltage is applied by the outcome mode, so that would be open loop in AC analysis. So finally, we have a input going up by if we input over 2 plus, and the other side go down by minus V in over 2, right? So this is AC ground. We have a load R1 and R2, so the AV would be what? GM times R1 or R2, right? If R1 and R2 same by R, right? So this is a self-feedback common mode amplifier. For this amplifier, let's check the output swing range. So at the proper bias, the half of the ISS over 2 and half IS over 2 will flow on both branches, and at bias condition, the node N will be set up by the VSG from the PMOS device. So VSG would be VTHP plus V overdrive voltage. In that case, the output is the bias. So that the max, since the Vn is fixed, so maximum voltage it can go at the output here with the Y here, the VDD minus overdrive voltage of the PMOS, right? That is the maximum voltage. What about the minimum voltage here? The minimum voltage it can go down would be input common mode voltage, input CM minus VTH, right? For ideal swing range, we want that to be one output to be in the middle of this output swing range, but the because of this self feedback, the output is output common mode is biased where? So at the feedback that would be here, that voltage would be VDD minus VSG. That would be what? VDD minus VTHP float plus V overdrive voltage here. So we have only for single sinusoidal output here, only range we can hear, we can see the sine wave amplitude would be the max sine wave amplitude would be what? Is limited to where? So VDD minus V overdrive P minus, right, that one. So if you calculate the VDD minus VTHP plus V overdrive P, right, so that would be cancel out, so VTHP, right? So the output swing without distortion, it can go up by VTHP and down by VTHP. So this kind of a simple self-feedback common feedback circuit provide us the reliable biasing, but at the cost of a reduced output swing. So this kind of a circuit provide us reliable bias, self-bias, the expense of reduced output swing. To separate the output biasing level and swing limitation issue, so we can drive that, we can change the biasing like this. So take out the common mode voltage and then use the amplifier and compare with the output reference voltage, use that like this. Then we can have the desired output range. The output common mode can be set by this provided the voltage, right? So in that way we can maximize this output swing range. By the negative feedback. Okay. There's another technique to have a gain boosting. Consider you can consider that only PMOS load, the diode connected PMOS load amplifier. In that case, we are sharing the bias current through biasing current for PMOS load and NMOS load, NMOS input device. So the gain would be GM1 times GM1 over GMP. So since we are sharing the current, bias currents, GM difference would not be that large, right? Because the GM definition, by definition, would be mu n 2 times mu n COX W over L times ID, right? So if you have a large gain, then you either have a different size or a different current, but for this kind of configuration you are sharing the current level, so only way to change the gain is the sizing. So we don't have a much the freedom, design freedom, by having this configuration. To have a higher gain than this, we can put the current source in parallel with the diode connected load, so that the current is flows by fraction than before. Then the current source, like 0.8 times ID, then we can change the ID through this diode connected load, so that we can easily change the GM of this diode connected load, so we can have a larger gain, right? For example, in this case, if you have a 0.2 current only, well, that would be the 1/4 of the, let's say, 0.15, right? 1/5 of the current compared to the previous case. Then how much gain or how much load impedance increase, that would be √5, right? Square root of 5 times larger 1/GM you can have, right, by having this arrangement, right? So you can have some design freedom to change the GM freely. So this is the current source in different. This is the differential amplifier configuration. We have a current source and diode connected load in parallel. So in that case, we always try to make that the current through this diode connected load would be smaller than the current source. In this example, current source is 0.8 times ISS over 2, and diode load would be ISS over 2 times 0.2, right? So this ISS is a tail current source. At bias, it will split on both, right? ISS over 2, right? Okay. So the overall gain on the right hand side, we can find that. So 1/GM, the load impedance, we can make it like 1/GM. RDP. RD would be 1/GMP. So overall gain would be GM of the input device times RD parallel with RON and ROP. So if you consider the ROP and RON, we can find that, we can drive that overall differential gain like that, okay? So far we just looked at the differential inputs and differential output. In some case, we want to drive the differential input and single-ended output, like this operation amplifier. So take the difference in gain and AV out. So V out would be AV times VP minus VN, right? So this kind of amplifier you can build. How? So first, for the input, you draw like the differential pair. So VP and VN. For the bottom, we have a transistor for current source, the bias. This is VB bias. And what about the load? For the load, we can construct transistor, PMOS transistor here, like this. Share the gate, and then take the current mirror, the diode connected load like that. And then take the output, V out. Let's find the gain of this amplifier. So V out would be for this kind of amplifier, we can find this for simplified analysis. For the input difference for the difference, so it will generate the differential current ID, and the gate will be ID over GM. The sourcing gate will be ID over GM. And this ID current will be replicated. So finally, the output, we have ID going into the output node and ID on additional ID coming out of the other side. So to find out gain, we use the big GM. To find the big, we use that AV equal times G, the big GM times R out. For simplicity, R out would be what? Would be here ROP and RON. So ROP, RON in parallel, and the big GM would be, so we for big GM, we take the output to ground it and see how much out coming out. That would be what ID times 2x ID will come out, right? So the input around the input network, so it would be easier to specify the input for Vi over 2 in plus Vi over 2, the other side minus V in over 2 for simple calculation. And then around the input network, we can say that so Vp minus Vn will be V in. Right, that would be what so V in that one. So starting so the that one. So and starting from the Vp, that would be minus ID over GM, additional minus ID over GM. That would be Vn. Finally, so ID would be what? GM over 2, right? ID, so Vp minus Vn, Vin would be 2ID over GM, right? So therefore, ID would be GM in over 2, right? So from 1 and 2, 1 and what? So this is 2 and 3, we can find that the big GM would be, that would be so what? Big GM times V in. So let's write down. So that would be what? ID would be GM times V in over 2, right, times 2, right? So that will be GM times V in. So the big GM would be what? So same as GM. So finally, so the big GM times V in. Finally, AV would be what? So big GM is a GM, and R out is ROP parallel with RON, right? Something like this. So because of the 2x larger current, we get this equation, right? So is there something wrong here? Right? Okay, right? So this is the differential input to single-ended output amplifier by having the current mirror load, right? For differential input and single-ended output circuit, you can compare two cases. One is the one is fully differential circuit. Let's use that the arrow notation. So VB bias, you only take the output, right? This is the case, and the one that we just learned is that current meter load, right? Like this. So if you look at that, here, for this kind of a circuit, if you look at the difference V out, then gain would be GMROP, and gain would be the differential gain. So differential input in versus diff out. In would be GM times RO, P and RON. But if you look at the single output over differential in, that's gonna be only half gain of that, right? But by having this kind of a mirror connection like this, even with the single-ended output, you get the gain. What? Diff to single output gain is GM times ROP times RON. Why? Because we are reusing the current, circulating current through this current mirror, right? So we improve the big GM. So big GM is improved by 2x, right? So big GM goes up by 2x, right? So that we were able to get this gain out of this circuit. Okay. Definitely, here the assumption is the WP over LP the same here, same size, and WN over NL, LN, and WN over LN. So this is the balance the circuit we are assuming here. So by having current meter load boost voltage gain by 2x, right? Okay. For differential input to single-ended output, another application is comparator. So unclock the comparator, we take the difference and generate the output. The input and an output relationship would be like this sharp transition like this. So whenever input is high and greater than 0, then generate the maximum voltage. If the other case generate the lowest voltage, that would be the 0 here. So this is the half VDD over 2 level, and then this would be around the 0 volt, right? So that's be the input also 0 volt. Okay, for this kind of a comparator design, we can use the same differential to single-ended amplifier structure, but for modern the deep submicron process, with the single-ended gain like this. So gain of this guy would be how much? so with the bias here around the GM times ROP and RON. This number is approximately around the 10, so this might be not enough for the comparator design that require much higher gain. So to improve the gain, we add additional stage, take out the output, and then put an additional source, common source amplifier there, and then share the current bias like this, and take out the output. So this is the two-stage amplifier. By itself, we can use that the comparator, high gain comparator. So this is another stage, GM times ROP parallel RON, right? 1 and 2. So we can add the second stage gain. This is the first stage gain. So we can get up to around 100, more than 100 gain easily out of this structure. Okay. One thing that note is that because that one, suppose that one is good for the output common mode level of this stage would be the near VDD, because this is a near VDD, because this is the first stage balance the differential pair. The left hand side node X and Y are around the similar voltage region or voltage range. So near X and Y and voltage Vx and Vy near VDD. So that would be easier to bias the PMOS input here. That's why we put a PMOS common source amplifier structure here, right? This is for easier biasing with the proper size. Okay. If you place the common source amplifier with the NMOS input, then you will have a huge overdrive voltage. In that case, you will have a very high current consumption. Okay, so this is the proper way of connecting these devices. Okay, if you are using some amplifier, two-stage amplifier with some Miller compensation here, that's gonna be another way of designing amplifier in a feedback analog loop. You can use that compensation, but without this, you can use this structure for comparator. So this is for the compensation. Frequency compensation, but we haven't yet frequency compensation. We had briefly touched upon that compensation before. This is for frequency compensation, okay, in analog amp, OPM. Okay.